So as we're going to be talking about ocean energy, if we were thinking about context, we like to provide context in this class, right? If we were thinking about our energy resources as like fruit, like watermelons of our clean energy transition would be things like solar and wind. Ocean energy would be what we would lovingly call it a pea or maybe a sesame seed. It is not something that's contributing a lot to the energy mix right now. It has potential, but in very localized locations. So there is investment and interest going on in it. But in terms of the amount of electricity it's providing, it's still very, very, very small. Much of ocean energy is still very much in the research and development stage. So what I'm really going to be doing today is kind of taking you through what are the different ways we could use ocean energy for energy resources, because there's kind of big categories. What's the potential, and what are the areas that are happening right now? Like I said, not a lot of it is contributing a lot to the grid. So we'll see some beautiful pictures too. This is from Maury Point and Pacifica, just looking down the coastline, and you can see some of what would be the energy resource here, like waves is one of the energy resources we're going to be talking about today. So big picture, it's like, what is the potential, what's happening, and what's the advantages and disadvantages? Because there's a lot of competing uses for our ocean spaces, whether that's for fisheries, shipping, recreation, and then of course offshore wind farms. So there's a lot of other uses for that space. So we're going to talk about some of those impacts as well as the environmental impacts of potential energy resources from ocean. You guys had a nice little short list of videos for today. Here we are in our renewable category. Ocean energy, for the most part, is a solar resource. And so us using it is not affecting the sun and how much energy it's providing to the planet. So our waves, our currents, our ocean thermal, those are all provided by the sun. We'll talk about the only one that isn't provided by the sun is tidal, which is provided by the moon. And again, our use of that doesn't impact the gravitational pull of the moon. It doesn't impact the resource itself. So it is a renewable resource, at least holistically. Okay, so I'm going to take you through some of the potential, the history, and then take you through the major categories of ocean energy. Kinetic, thermal, and chemical are kind of the big categories, and we'll talk about each of them. So we have it in our renewable category because we're not affecting the resource by using it, but there's a lot of interesting drivers and barriers. So it's abundant and renewable. There's no greenhouse gas emissions. There's no air pollution when we're using the ocean as a resource, so we can talk about zero carbon. Water is way more dense than air. So if we're thinking about something like a resource, we're putting basically like a wind turbine under the water to make use of like an ocean current or ocean tidal, you get a lot more energy out of a smaller unit because the water is so much more dense, or out of slower moving water than you would with air. So we go back and look at the equation that we had for our wind turbines. You can use that for ocean too. And that density factor can mean you can extract a lot more energy from slower moving water because it's more dense. Tidal energy in particular is very predictable. So this can be an advantage. We talk about the variability of a lot of our renewable resources, but we can manage that variability if we know when it's going to be variable. Tidal, we know exactly how high it's going to be and what time. So that's a very predictable resource. A lot of demand centers are coastal. So we mentioned that not all the countries have coastal resources, but the ones that do, a lot of times big cities, high demand centers are going to be on the coastlines. Islands, which have challenges having a lot of good resources, often are going to have some of these good ocean resources. So it can be something that complements their other resources. And that's kind of a minor one. Okay, so barriers, you mentioned it, NIMBY, right? That's going to be a problem with using our ocean resource, being at site specific, which you guys talked about. Putting things in the ocean, it's a really harsh environment. It's salt water, there's storms, those waves can get really big. Even if they're normally kind of small, they can get really big. So that is really hard on equipment. It's hard on boats and ships. It's going to be hard on equipment. So that's a major challenge with ocean energy. Weather patterns, when it's going to happen, that makes it really variable. Much of the technology is in the pilot stages. And what that means is that a lot of these we haven't coalesced around a design that really works. And so we can't even begin to scale until we've coalesced around a design that really has the longevity and the energy extraction that we're looking for. And so that means it's very much in the early stages, not a lot of commercial development. And where we have commercial development, it's not cost competitive often with other resources. So it takes a lot of public investment and private investment for that. Okay, and then we mentioned the environmental concerns and the competing uses. So lots of drivers, lots of barriers. It's an interesting small thing, which is why we're spending a kind of a shorter lecture on it. So what is the potential? So I mentioned there's kind of these three big categories. Kinetic is in the blue, thermal is in the red, salinity is in the yellow. Huge theoretical potential if you're looking at the whole planet. So you can kind of get a sense of what that potential is. But where the action is happening is very, very small scale. And so a few things to point out here. Most of the grid-connected ocean energy is from 2 installations that total 500 megawatts. That's like the stuff that's consistently providing of energy to the grid. We also have been doing more in wave and other types of tidal, more like wind turbines underwater. These megawatts here, they go up and down because a lot of those systems, even if they're grid connected, sometimes they're there for 1, 2, 3 years and then they get swapped out and then it's something else. So still a lot of that is very much in the demonstration phase. And so we'll see these numbers change up and down, but not really growing because it's such a challenging environment to operate in. And then you can see these last 2 categories is very, very small in terms of what's happening. So we'll talk through what all those categories mean. But just to give you a sense of scale, these are our renewable power generation resources. Here's our ocean energy compared to kind of the other renewable resources. And so it's, like I said, it's an interesting P because there's a lot of interesting things going on in it. But it's very early stages, very much research and development. So we talked about this a lot already, but just to give you a summary of all of the challenges, this applies to all of those different kinds of ocean energy resources. In terms of wildlife, local effects, you can change how water is moving around, so that can impact the ecosystem. You can change how the sand is moving around, so that can impact shorelines, for example. You can have impacts on temperature, depending on the resource. And so that can impact ecosystems. And then, of course, the competition for other resources, and then the harsh environment that makes it really hard for things to last. So lots that are very challenging for ocean energy. So let's talk about each one in a little bit more detail. So let's start with Kinetic, because that's where we have those 2 big systems. It's providing the most electricity to the grid right now from ocean energy. So the first category of Kinetic we'll talk about is tidal. So tidal energy systems are the most prominent. They're like I said, the most predictable. We know when and where tides are going to happen, but it's not dispatchable in the sense that we can't change when that tide is going to happen. So we just have to manage the grid around when the tides are available. Of course, tides are primarily driven by the moon, also interact a little bit with the sun, but we know exactly when and how that happens and where the tides are going to be the largest. So to give a sense of how do we measure the tides when we're talking about ocean energy, there's kind of 2 key terms we talk about: range and volume. This is very much similar to what we talked about in hydroelectricity, right? When we're talking about range or head, that's how high your tide is, and how much water you have. That's your flow rate. And remember, head matters a lot for how much energy can we extract, and the volume or the flow can really impact the timing of that extraction, right? And so you can see some of the red areas on this map is where we have a lot of tidal range. And then you get even bigger tides in places where the coastline has particular geography that can lead to things like sloshing and things like that can get even higher tides in some of those high tide areas. Okay, one of the biggest tides, just because it's fun to talk about, is Bay of Fundy in Nova Scotia. I got the chance to go just randomly. You can see the Bay of Fundy is kind of this narrow inlet. Like I said, sometimes we get the biggest tidal ranges because of the geography of the coastline. And so here it has a 16-meter tide. And you literally see a wave of water go in and out of this bay. You can do this tidal bore rafting. It's one of the recreation things they do on this, because you can actually ride that wave in or out of the bay, but you can get a sense of how big that is. And so in theory, you could put a dam across the Bay of Fundy, and that would be basically a big tidal resource, right? Because you have that big head from the bay and that water sloshing in and out. Now, we have small systems, and I'll show you some small systems in the Bay of Fundy, but obviously there would be a lot of controversy with that for environmental reasons. When you dam it, you're blocking off access for wildlife into there. You obviously would end any sort of recreation like this. That's one of the tourist attractions for the Bay of Fundy, et cetera. So what are they doing? This was one company that was looking at doing some sort of a floating, basically a floating platform that would have kind of like wind turbines underwater off the floating platform in the Bay of Fundy. Because it's not a dam, it wouldn't block things. It would just kind of extract tidal currents as they're flowing by. But one of the big challenges, and the reason I highlight this, is the policy situation. So this company actually installed this, but it didn't get long-term permitting. And so it basically wasn't able to extend its permit and filed for bankruptcy recently. So one of the challenges with ocean energy, because it's so small scale, it's still research and development scale, there isn't a lot of very set, easy pathways for permitting. And so permitting can be a major roadblock for a lot of these technologies. So what is the potential for tidal energy in the United States? It's in the orange here on this chart. It's a very localized resource. So orange is kind of where some of the best tidal potential is in the United States. And you can see Alaska is kind of the biggest place. It's going to be the biggest place for a lot of our ocean energy resources, but it's that orange space. If you made use of all of this, it would be about 5% of US electricity use. So not insignificant if you're thinking about locally using it for electricity production, but not a huge resource, and much of that is in pretty remote locations like Alaska. Okay, so how does it work? So the easiest way in those two big installations is just a dam over an inlet, right? So we can basically use a hydroelectric dam. You can allow the tide to come in and run through a turbine. Sometimes that turbine can flow both ways. So you're extracting energy as it comes in, you build up water behind it, and then you let the water flow back out after the tide has come back down, right? And so you have that head, and you're able to take advantage of that. Those two systems are shown here. One is in France. That's the oldest one. So it was built in the 60s. And then this one was built a little bit more recently, over a decade ago in Korea. The guess was that this was made slightly larger so they could have the largest one of the two that are in existence in the world. But this is kind of it. These are the biggest installations for ocean energy today. And you can see both of them, they act as roadways across inlets, and they operate very much like a hydroelectric dam, only it's using tidal energy instead. There's a very small installation. This is actually a former TA of ours that went and visited this. This is off the Bay of Fundy. It's just off one of the little side inlets, so it isn't a lot of energy. You can see it's only about 20 megawatts. It's a very small kind of test system that they were doing in the Bay of Fundy. Okay, the other way we can make use of tidal currents is to do something more like a wind turbine underwater, right? Because the water is flowing. Now, the best locations for tidal current in this kind of setup is places where that tide is being squeezed between places. So if you have a tide that's being squeezed between like a shoreline in an island, for example, this is what we see in Scotland, it's going to get you higher velocities because you're squeezing that tide. And so now it's not so much the head that matters, it's how fast that flow is. What is the flow rate? You can see we've had a lot of different designs, just like we saw with wind turbines in the early days. I would say the community is really kind of coalescing around a horizontal axis turbine. So something that looks very similar to a wind turbine that we're putting underwater. You can see this one here. So very, very similar. This is the other place where we're seeing a little bit of electricity production. Much of that in Scotland, but other places are also kind of looking at it. This is what Scotland's doing. So Magen is kind of their main project. And you can see the little wind turbines going in. This is a rendering of what it looks like. But they're continuing to grow this project. So it can be very modular, and they can put them in the different sites. One of the things that's been important about this site is checking the impact on wildlife. So in this area, there's a large seal population, for example. And so one of the things that they're monitoring is how this impacts the seal population. They haven't found that there's any sort of risk about impact. The seals just kind of avoid this space, but it's definitely moved where the seals would normally be because they avoid, it's noisy, they don't like the wind turbines underwater, and so they tend to avoid this area. So in that sense, it's not directly impacting them, but it's certainly impacting where they would live and their habitat where they would hunt. So they are kind of monitoring for that. In the US, we've had some interesting devices. I looked up this one because you can kind of get a sense of how long these research and development projects really take. Again, there isn't really a streamlined permitting process. And so they've had different designs. They're starting other designs. These are more like horizontal axis wind turbines that we see, only now they're doing it underwater. And they're also looking at things that are not as permanent, so that you might be able to put it like in a river or something, have a floating platform. You want something that's easy for maintenance. So you want something you can either get in and out, or you have a platform where you can get in and out, something, because these are pretty harsh environments to deal with. Okay, final form of kinetic energy would be ocean currents. So ocean currents are different than tides, right? Our tides are driven by the sun and the moon. Ocean currents are driven by the uneven heating of the ocean. They tend to be larger scale. Like we have big ocean currents, right? The Gulf Stream, for example, that comes from the Gulf of Mexico, off the Florida coast. That's what keeps Europe warmer than Canada, right? And so these are very important for big weather patterns on our planet. Although they carry a lot of energy, they tend to be pretty slow in the sense of something like a tidal current would be much faster. So it's pretty diffuse in terms of how much energy those currents are carrying. And there's concern is like, we don't really want to mess with them. We don't want to slow them down and extract a lot of that energy because it could have significant impacts on ocean and weather patterns, right? So there's been some very, very small scale research space stuff. There's a little bit going on in Japan in one of their ocean currents, but it's not a lot going on in the space. So it's hard to extract a lot of energy from ocean currents. And we already have concerns about how climate change is impacting them and impacting weather. So not a lot going on there. What is the potential? So this just gives you a sense of the US. Our biggest one is that ocean current from the Gulf Coast, but it's small. It's much smaller than kind of the wave and the tidal potential. So now we're going to talk about waves. So waves are kind of fun. Okay, I love this picture. This is literally a magazine cover from the 1930s. And the wave energy devices that people are still designing are kind of the same. This is again is a space that there's been a lot of great ideas and nothing lasts very long. The challenge with taking advantage of wave energy in particular is that it's really hard on the mechanical systems that you're putting in the waves. And so all sorts of different designs, they last 1, 2, 3 years, and then they're breaking, they're falling apart. They just don't have longevity in the environment. And so this is a space where there's a lot of cool ideas, but not a lot that's really providing any electricity to the grid. So where are our their best wave resources? This gives you a sense of where those are located. It's kind of like the best surfing sites. So, you know, west coast of Australia, a little bit off of Alaska, and the west coast of North America, places like that. When we talk about wave power, now we talk about it in kilowatts per length of wave. That's just how they rate that. And so that's what these numbers are. They're in power per length of wave. Looking at, again, at our map of the United States, our wave is this darker blue. So there's a lot more wave potential, but again, there's also a lot of competing uses for waves. So how do we take advantage of our wave resources? There's kind of three big categories. There's something called wave surge or focusing. There's something called oscillating, water column, and then there's something called floating pitch and pitching. Okay, so for each of those. Our wave surge or focusing, this is a device that you might think about having, and you can have it either on the shore or floating in the water, where the wave crashes over the top and then it flows back out through a turbine. So you can do that, like I said, on the shoreline. You can have a wave crash over something and then flow back out through a turbine, or you can do it in a floating platform like it's showing there, but you're basically using a turbine and the water runs back out through it after it's crashed over. Oscillating water column, which we have a couple of these in operation. Here you're using a special kind of turbine that spins one direction no matter which direction the flow is going. And so what that wave is now doing is pushing air through the turbine and then pulling air back through the turbine as it goes up and down. So again, you would have this on the coastline. The wave would push air up through the turbine, pull air back through the turbine spinning the same way the whole time and producing electricity. The fun ones are these floating and pitching devices where you're trying to take advantage of that wave and turn it into something that's either pumping water or creating electricity. Now, something to think about for wave, because a lot of people may not think about this. It's very different from currents because it's not actually a flow of water. Wave energy is wave energy flowing through water, and it's often kind of in a circular motion where this particle hits this particle, hits this particle. So you have energy flowing through the water, but the water itself isn't flowing. It's an up and down motion in the water. And so you have to translate that up and down motion or that circular motion into something that's flowing or something like that. And so that's how we're making use of that. So wave energy is kind of flowing through the water. Okay, so let's look at some fun pictures, some startups. This one is a new one in Scotland where they have this beautiful rendering and one that they're putting in. This is another one that goes on docks. It's taking advantage of the up and down motion of waves. We've had fun things like the Mighty Whale that was a floating oscillating water column that worked for a while. You can kind of see some pictures of it there. This was a fun one. These are like giant sausages that moved back and forth. Again, have lasted for a few years out in the water, and then that company went bankrupt. This is something more like a buoy that goes up and down. This is another buoy type system. You can either have them above water or below the surface of the water. Again, they're just taking advantage of that wave motion that's moving through the water. So you can read more about where those last. This one, the idea was that you can move it around, so it's its own platform, and it could line up and dock at different places to provide electricity to local grids. One of the big things that in wave energy is, like I said, it's still in the research and development stage. So the access to ocean sites to do this research is very important. And so in the United States, we have something called PAC-WAVE. We have actually 2 sites off the coast of Oregon, both a north site and a south site. And the south site actually is grid connected. This is where a lot of offshore wind energy research goes on, especially when we start thinking about floating platforms. We have some professors here that work with some other professors at Oregon State to do that. And then, offshore wave energy or mostly wave energy systems as well. And so the nice thing about having these sites set aside is it makes that, excuse me, makes that permitting, at least for the testing stages, easier, right? So you don't have to do a lot of like, can I put this somewhere? The site's already permitted for these research stages. And so it helps them kind of go through kind of the early stages of design a lot more easily because it has that permitting already done. Okay, next we're going to talk about thermal. So thermal, or called OTEC, or ocean thermal energy conversion. These systems are just like our steam cycle power plants, but more like our binary geothermal power plants. What we're doing is it's a heat engine, and we're taking advantage of the fact that the surface of the ocean is warmer than the deep ocean because the sun is warming the surface. And you can take advantage of that temperature difference and run basically a binary cycle power plant, something that runs on lower temperatures than steam, right? Just like we see with our geothermal binary. So this is a demonstration plant. You can see it's really small. It's 100 kilowatts. In Hawaii, that is running and has been running for a long time, an ocean thermal energy conversion system. So this just gives you a sense of what that looks like. Basically, we're just taking water off the top of the ocean for the warm. That's just your hot source, and water from the deep ocean as your cold sink. And you need places where there is a big enough temperature difference for that to happen. So the best temperature difference you can see are gonna be places that are closer to the equator. So this could be a place where there are islands or things or coastal areas close to the equator that have a big enough temperature difference in order to be able to run your heat engine. The bigger temperature difference, the more efficient your system is going to be, the more energy you have that you can extract. It needs to at least be 20 degrees different between that hot and that cold, that deep ocean. So what is our ocean thermal potential in the US? Most of it is here in Hawaii. You can see that there. There's a tiny bit here in the Gulf Coast, but if anybody's ever been to the Gulf of America, it's really shallow. And so it actually is all warm. And so there isn't, you almost need a cold sink that's better than the Gulf Coast area because you don't have a lot of temperature difference between the surface and the deep ocean because it's just not that deep there. Hawaii, on the other hand, has a lot of temperature difference between the surface and the deep ocean. So a little bit better. And then you can see a lot of islands that have potential for ocean thermal because a lot of them are close to the equator where you're getting pretty warm temperatures. Okay, how does it work? Works just like the binary cycle that we talked about for geothermal. Right, so you have warm seawater, that's what's evaporating your working fluid. So it has to be something that evaporates at pretty low, relatively low temperatures because it's just warm seawater. You're running that through a turbine to make electricity, and then you're using cold seawater as your cooling water or your cold sink, and you're running basically a binary cycle. And so that's what they're doing at this little system in Hawaii. That's a closed loop system. There is also something called an open loop system. To my knowledge, there isn't an open loop system in operation today, but it's been something that's been done in the past. In this case, what you're doing is you're actually using the warm seawater as the working fluid. You're just doing it at a lower pressure so that you're able to make it vaporize, even at those relatively low temperatures. The advantage of this system is that it does make fresh water. So by evaporating that warm seawater, you're making fresh water. So you get like kind of a bonus of freshwater output. But the challenge is that you also get super salty seawater that you have to deal with. And putting that just back in the ocean can have impacts on the ecosystem. And so that can be a challenge with that system. Last category is our chemical or salinity gradient type. This type of ocean energy, we just kind of put it in here for completeness. There isn't a lot of research going on this. Basically, you can use the fact that saltwater and freshwater have different osmotic pressures as an energy resource. It's a pretty diffuse energy resource, but you can use it because you basically have a head difference between freshwater and saltwater. So places where big rivers are going into the ocean would be places where you could take advantage of the difference between the freshwater and the saltwater from the ocean, and theoretically use this for electricity, but there really isn't a lot of research going on in this. It's not really thought of as a major potential energy resource. All right, so what's going to happen with ocean energy, our beautiful ocean pictures? Investment in ocean energy is really small. This is a little bit old. This is 2020 data because it's hard to get the more recent data, but it gives you just a sense of the different in investment in things like solar, wind, even like biomass or small-scale hydro compared to ocean power. So not a lot of investment. It's not a lot at commercial scale. There's a lot of challenges in terms of the environment it has. And it doesn't even end up on our LCOE chart, but the DOE has done some estimates of it. And even those estimates, when we got to commercial scale, are a lot higher than our other more developed energy resources. There is some areas that have been approved for permitting, and this permitting of these different types are still in place. But again, there's not a lot of action going on. So, summary, big potential, a lot of hurdles, very much emerging technologies.